Good evening, everyone. Welcome to Science at the Theater, which is sponsored by Friends of Berkeley Lab and is co-sponsored by the Berkeley Energy Resources Collaborative. And we want to thank all of you coming out for a night on which the Giants are playing. My name is Dan Krotz. I'm in the lab's Public Affairs Department. And this is the second of 3 in our Fall Science at the Theater series, which we've entitled Get Smart About Carbon. And we're calling it that because we want you to come away from these talks with a better understanding of the causes of climate change, what scientists are doing to mitigate it, and definitely most importantly, what you can do to take action. We hope tonight's topic, cool cities, cool planets, will do just that. For the next hour, you'll hear how cool roofs can be used to help you save money, cool your city, and most importantly, help fight climate change. It's actually the perfect think globally, act locally kind of story, and it's central to the lab's principal mission of providing technological solutions to some of the most urgent problems facing the nation and the world today. We are very pleased also to have with us a person who really sets the standard to that approach, providing technological solutions to urgent problems facing the nation. And that person is Art Rosenfeld, sitting over there in the middle. As many of you probably know, he's seen by many as the godfather of energy efficiency, and in a decades-long career, he's credited with billions of dollars, with a B, in energy savings in California and beyond. He started out as a physicist, but during the 1973 energy crisis, he decided to do something about it, and he literally walked around a building at the lab at night, turning off lights one by one to save energy. And he has been doing something about it ever since. He started a buildings energy efficiency program at the lab, which has gone on to great renown. And he just finished a 10-year stint on the California Energy Commission earlier this year. Among his many accolades, Art actually has a unit of electricity savings named after him. A Rosenfeld is the electricity savings of 3 billion kilowatt hours per year, which is the amount needed to replace the annual generation of a 500 megawatt modern power plant. And also the term Rosenfeld effect is used to explain the phenomena in which California's per capita energy usage has essentially remained flat since the mid-1970s, while the rest of the US has gone up by about 50%. So much of that flattening is attributed to Art's work. Also on the panel is Ronnen Levinson. He's a staff scientist at Berkeley Lab and acting leader of the Heat Island Group. He has developed cool roofing and paving materials and helped bring cool roof requirements into building energy efficiency standards. We also have Melvin Pomerantz, a member of Berkeley Lab's Heat Island Group, trained as a physicist at UC Berkeley. He specializes in research on making cooler pavements and evaluating their effects. A bit of housekeeping before we get into the talks. Each presenter will speak for roughly 15 minutes, and then we'll open it up for questions. So we'll fan out into the audience and wait for a microphone. Please keep your questions short and crisp so everybody has time to ask a question. I'm sure there's going to be quite a few. I hope this doesn't happen, but in the event of an emergency, the exits or the entrances in which you came are your emergency exits. One here, and one here. And also, before you leave, please fill out an audience survey and leave those with a lab volunteer in the lobby. It really helps us improve and fine-tune and tweak Science at Theater events in the future. So, without any further ado, please welcome our first speaker, Melvin Pomerantz.
Thank you very much, and thank you for coming. What I'm going to talk about is a very familiar experience to all of you, and that is the fact that when you go into the center of a city, it's a lot hotter than it is in the suburbs. I once lived near New York City, and it was amazing. You would drive into the city, and it was just hot and steamy. Drive out toward Westchester, where I was living, and the trees are there, and it's cool, and it was a shocking transition as you leave the city. So that effect, namely that the temperature here is very different in the suburbs or the rural areas. And as you get toward the center, the temperature is shown here in Fahrenheit, tends to be anywhere from, say, 5, 7 degrees Fahrenheit higher in the center of the city than it is where the trees are still there. We simply replace trees, which are cool, the forests are pleasant and cool, with man-made surfaces, which tend to be dark and tend to be hot. And so, well, in addition, there's a lot more people concentrated in the center of the city. That's another effect. But that we can't do much about. I mean, people want to live in the center and work in the center of cities. But there is something we can do about the kind of surfaces we put in the city. And that's going to be the gist of this talk. What can we do to kind of relieve this excess heating in the center of cities, or where the cities are built up? This has not only an effect of discomfort, there's real economic problem here too. What is shown here is the electric power demand in Sacramento. We got this data from them. This is SMUD, the Sacramento Municipal Utility District. On a day in July 1999, this was one of their peak days. We picked it not to be typical, but it's a hot day. It went up to, here you see, about 107 degrees that day. And what we show here is their demand starting at, say, 1 a.m. in the morning, 2, 3, 4, 5. The temperature was going down. At about 6 a.m., the sun starts to rise. People wake up. They start turning on electricity, their air conditioners. And as the day goes on, it gets hotter and hotter. And the demand for electricity gets higher and higher until at noon, it's up around 2,500 megawatts. And then by 6 p.m., it's up here around 2,700, peaks out, and sort of lingers there as the day cools down. And finally, it cools down, and people sort of go to sleep and turn off their air conditioners a little bit. What this means is that these are indicating the number of power plants you would need to generate this electricity. Each power plant being a typical one that was named after, in the art, Rosenfeld effect, a 500 megawatt power plant. So to get this much power, you need at least 5 power plants. Close to 6, actually, because 5 will produce you 2,500. So 5.5 power plants. But you see, the actual power that's being used on a January day is a lot less, half as much. So that means that the power company has to have in reserve all these power plants, which means that there's a capital expense to have power plants that you built, but you're not using much of the year. So that's a drag. And then, moreover, these power plants that they finally turn on are usually the least efficient, most polluting power plants, because you use your most efficient ones at first. So as you turn on your old plants, you create more pollution, and you're using more energy, and it's an unfortunate situation. Now, the heat island effect is actually relatively small. Where's my arrow gone? Where has my arrow gone? All right, but the heat island effect is typically a few degrees. So what can we do? Well, we can possibly slide down this curve a degree or two. That heat island effect was about 5 to 7 degrees. If we can even slide down a few degrees, we can cut off the top of this curve and save much power. The other thing we do is cut down on pollution. And another effect that goes on is the fact that when things get very hot, there are actually deaths caused by this excess heating. The one case that we have some pretty good data on is in Chicago in 1995. There were 700 or something, 39 deaths attributed to the heat wave that they had. And interestingly, almost all of them, like 700 of those deaths, occurred in the top floor of black roofed buildings that didn't have air conditioning. So those roofs were very, very hot in the sun. If they had thought to whiten the roof, they could have perhaps saved those people's lives. So there's a health issue here also. And so the question is now, what can we do about it? So the basic physics question that some of us are interested in is, how is the air heated in the first place? And it's interesting that the sunlight coming in from the sun does not heat the air directly. I could give you a quick proof of that. When you came into this building, you could look out and see the Golden Gate Bridge. The Golden Gate Bridge is 9 miles from here as the crow flies. So that means that what has happened is that sunlight has come from the sun. When you look in daylight, sunlight has come from the sun, it hits the bridge, it comes to your eye through 9 miles of air. That's twice the thickness of our atmosphere. And yet you can see the bridge very clearly on a clear day. So that's kind of an indication that sunlight travels very well through the atmosphere. And in fact, we'll show real data later about that. So how is the air heated? Well, the way it's heated is the fact that there are opaque surfaces, surfaces that cast a shadow. So what's happened is that the light comes in from the sun, it strikes the surface. Now this is a light-colored surface. Most of the light is coming back. But some of it stays in the surface, and that much which stays in the surface heats the surface. And then the air comes along and touches that warm surface, the hot surface, and the air gets warm from that. So this is the clue of how we can attack the problem, because what's going on is that the surface is acting as kind of a converter of sunlight into heat of the air. So if we can get a handle on the surface, we can get a handle on how hot the air gets. The other feature as well is that not only does the roof or pavement get hot, which is actually bad for the roof and the pavement. You see, because it causes the roof and pavement to deteriorate faster if it gets hot. Moreover, if you have a building underneath the roof, that heat that's been absorbed by the roof, that heat travels into the building, and then you have to turn on your air conditioner in some places. Berkeley is an exception. We're lucky. We have the nice, cool atmosphere too. But you go to Sacramento, and it would be impossible to live there if you didn't have air conditioning. So the point is that it's very much advantageous. Also, pavements suffer if it gets too hot. One of the things that designers of pavements worry about is how hot is that pavement going to get. And if it gets very hot, they have to make a better pavement to handle the heat and the deterioration that the heat causes. So there's an extra expense, which we can avoid if we can possibly make the pavement cooler. So one way of characterizing this cooling of the pavement is to study what's called the solar reflectance. What is the ratio of the light that's reflected compared to the light that's come in? That number is something between zero reflectance, a scale of 0, would mean zero reflectance, everything is absorbed, it's black. If you have no light coming out, it's black. On the other hand, if all the light came out, it would be very white. This is the light that comes in, comes out. That's 100% reflecting, solar reflectance. And clearly, if the light is reflected and not caught in the material, it's cooler. So what we're looking for is materials of higher solar reflectance. And indeed, that theory is borne out. We've done experiments, others have too, of the temperature rise. That is, how much hotter is the surface than the air around it. And if the reflectance is very high, like 100%, like a white surface, it rises a little bit, 5 degrees centigrade, which is half as much as what we Fahrenheit. The point is that also if you increase the solar reflectance, or decrease it rather, down to about 0, in other words, it's very black, it's hardly reflecting at all, like black paint, the temperature can rise 50 degrees, which is something like 80 or 90 Fahrenheit. So above the ambient air, that's your cat on a hot tin roof, really. I mean, you don't want that. So our goal is to try to urge people to use lighter colored materials or find new light colored materials that will make these lower temperatures. And that's the gist of our talk. There's another feature, and that is that once the surface is warm, like the Earth gets warmed by the sun, it also radiates, but it radiates at a different place. I'm fond of telling my students, my male students, tell your girlfriend that she glows. It's true, physically she glows in the infrared, I'm afraid. So you won't see her in the dark, but she does radiate. And she radiates at a wavelength around in here, whereas the sun is radiating 20 times higher in frequency or shorter wavelengths by a 20th. Now here's what I said before, and that is that the sunlight passes through. This is the absorption by the atmosphere. You see, absorption is extremely low. It's one of the reasons our planet is so great. Our atmosphere allows the sunlight to pass through. Sunlight. But once it gets converted to this kind of light, there are gases in the air like carbon dioxide, oxygen, water, which absorb this thermal radiation, which we call thermal infrared, and that keeps, it's like a blanket. And this is the atmospheric greenhouse effect, where this light coming out of the Earth and us is blocked by the gases in the atmosphere. And if you put in too much of these gases, like we're trying to prevent, like carbon dioxide, we increase the absorption and we can heat the Earth by that reason. That's the global warming problem. So the gist of that problem is that if we can prevent the light from sticking in the surfaces, we will reduce this amount of thermal radiation, we'll reduce the amount that's trapped, we'll reduce the greenhouse effect, and if we reduce the greenhouse effect, we keep the planet a bit cooler. And Art Rosenfeld will talk in great detail about that. So here is our task. What can we make cooler? And there are, in fact, many dark surfaces in a typical city. Here is a patch of Sacramento, and we actually measured just what's going on there. Some dark surfaces, about 39% of the surface as seen from the sky is pavements, and about 20%, 19% are roofs, usually dark. Now, vegetation is good, and Sacramento has a program for putting in more and more vegetation. But our job here that we'll talk about is how do we make roofs and pavements cooler, namely more reflective of light. So this is the introduction to the rest of the talk. Namely, Ronnen Levinson, Dr. Levinson, will talk about how cooler roofs on top of a building directly prevent heat from getting into the building. It reduces the air conditioning that that building needs, which reduces the demand at the power plant, which we talked about, which means less energy is consumed, less carbon dioxide is generated, and those nasty compounds often turn into ozone, which is bad for your health. So Ronan will talk about that. I'll mention the other side of it, namely heating the outdoor air. Pavements and roofs also heat the outside air. If we can make them cooler, we reduce that outside air temperature ever so slightly, a few degrees, but it can matter. So what that does is reduce the demand inside the house because the outside is cooler. And again, we go through this cycle of reducing electricity demand, energy consumed, pollutants. The other thing that happens if the outside air is cooler is that area sources like trees emit fewer of their organic things. The part of the tree that you smell, that can actually be part of pollution. It gets converted into ozone. And the other thing that happens if you reduce the outside air temperature is the reactions that are producing these bad chemicals are slowed down. So you can actually get less ozone. So this is the outline of the talk, and I will then, and this thing that I mentioned that Art Rosenfeld will talk about is that if indeed you reflect more of the sunlight, it's as though you took away some of that blanket because the planet will get cooler. The sunlight will travel right out. And you know that because you can go to Google and ask for the satellite view and see your own house. So that means that the sunlight has hit your house and has gone back up to a satellite and passed through the atmosphere. So if you leave it as sunlight, it'll get out very well. So that's what we're trying to do. On the other hand, the other way of getting the air to be cooler is just to take the greenhouse gases out. So one offset is sort of equivalent to the other as far as heating the planet. And Art will give us his ideas on that. So with that, I think I turn it over to Dr. Levinson.
I'm going to take you on a little cool roof safari. In other words, what would you see? What might you see? Well, here in North America, we certainly have cool roofs, and they're usually white roofs. You might find them on a commercial building because those roofs usually can't be seen from the street. And a white roof on a commercial building is terrific. When new, it could reflect about 80% of the sunlight that strikes it, and it will really help keep that building's use of air conditioning down. Or if it's not air conditioned, it will make it more comfortable on the top floor. Now, in some other parts of the world, you might see white surfaces on pitched roofs. It's not really a North American aesthetic outside of places like Florida, but this is a picture from Bermuda, where they do have a history of white roofs everywhere. And another possibility that you might see here in North America is the cool colored roof. Some kinds of roofing material happen to be naturally reflective to sunlight, and others are reflective to sunlight because you've engineered them that way. Now, if you have a white surface on a flat roof, most usually on a commercial building, these have pretty long operating hours, not all that much insulation in the roofing assembly, you could reduce your annual air conditioning energy use by about 15%. If you have a white surface on a pitched roof, then your savings of air conditioning over the course of a year is about 10%. Why? Well, mostly because when you have a pitched roof, it's easier to put insulation into your roofing assembly, and so less heat would tend to flow into the building. If you have a cool colored roof, like this lovely red clay tile roof that's shown here, well, your savings are about half as good on a white roof, and that's because approximately the cool colored roof is about half as reflective as the white roof. Now, we've asked the question, what would happen if you were to implement a broad program of cool roofs on buildings in the US? And right here, I'm going to talk about what would happen if you put white roofs on 80% of the commercial buildings that we have. Why 80%? Well, some of them are already white, so we're being a little bit conservative there. Now, the idea is your typical commercial building might have a gray roof that reflects about 20% of sunlight. And you could put on a white roof that, when new and shiny, or bright anyway, would reflect about 80% of sunlight. But after it gets soiled, it might reflect 55%, 60% of sunlight. Well, we assume from day one that it got soiled because we like our numbers to stand up. And what we found is if you take that 2.1 billion square meters, you can multiply by 10 to get square feet, of roof that represents 80% of the roofs on commercial buildings in the US, well, each year you'd save over $700 million on your utility bills, and you would reduce emission of carbon from power plants enough to be the equivalent of taking over 1 million cars off the road. Or if you want to think about it in terms of nitrogen oxide, which is a precursor to ozone and smog that Mel was talking about, well, that's the equivalent of taking over 500,000 cars off the road. Plus, there are savings from things like sulfur dioxide and mercury. But those I can't equate to cars, so I kind of focus on the first two. Now, over the lifetime of a roof, and a roof is typically around for 20 years, the energy savings that you would attain in those 20 years would have a present value, meaning it's what it would be worth right now today, because energy savings in the future aren't worth quite as much as energy savings that you incur, say, in the first year. Well, nationally, that would give you $11 billion worth of savings. Now, for the US economy, $11 billion maybe isn't a whole lot of money, until you realize that, especially for commercial buildings where your choice is maybe a gray or a black roof or a white roof, there's no extra cost choosing a white roof when it comes time to replace the roof for ordinary maintenance. Typical roof lasts about 20 years, which means that each year you're replacing about 5% of the US roofing stock. So this is free money, and we all like free money. But white roofs aren't going to work for every building because we just don't accept white roofs on those that you can see from the street. Except in Florida, where they do, and we're going to show you some photos later. So I'm going to talk a little bit about what can we do for those roofs that are going to be seen from the street. And the first step is to understand that your eye is very well attuned to see sunlight, but not all of sunlight. I've got a little graph here, and I've broken up the solar spectrum into 3 parts. In the middle here, which I've colored green, this is visible sunlight, and this is what you see with your eye. Over here to the left, this little narrower band, that's ultraviolet radiation. That is very important stuff. It makes colors fade, could give you skin cancer, generally damages things. But truth is there isn't all that much solar energy in the ultraviolet spectrum. But if we look out to the right, here's a portion of the near infrared that we call, well, it's a portion of the infrared that we call the near infrared, and it makes up nearly half of the energy in sunlight. Well, why do we care? Because you can't see that. So it doesn't matter how much near infrared light a surface reflects, that does not change the appearance. So what you could cleverly do is say, okay, we will have the surface reflect in the visible part of the solar spectrum the way that it's needed to make it look the way that you want. But maybe we could do a good job of reflecting these invisible patches of light out here in the ultraviolet and the near infrared. Well, it turns out that it's very hard to make a surface reflect in the ultraviolet unless it's a bare, shiny metal. Just most surfaces don't. So we kind of write that off. And we focus instead on this nearly half of sunlight that is at wavelengths longer than what the eye can see. And we try to make surfaces reflect as much as possible in that part of the spectrum. Here's a little graph that tries to put a little bit of data to that idea. If I have a white roof here, and this is a brand spanking new white roof on some sort of a box store, and I were to measure its reflectance as a function of wavelength over the solar spectrum, and this yellow curve here, that's that solar spectrum that I showed in the last slide. Well, we see that in the visible, it's very reflective, and of course, that's what your eye is telling you, and it looks bright white. Also, though, at these longer wavelengths, it is still pretty reflective. I mean, you don't know that a priori, but you can measure it, and if you were to touch it, you would feel, hey, this is pretty cool. And in fact, a bright white surface reflects over 80% of sunlight, like this white roof here. Now, at the other end, of course, you could have a black surface that reflects almost nothing, but I'm being a little more realistic because there aren't that many black roofs. They tend to be a little bit more gray. Well, here's a gray roof, and this is reflecting about 25% of the sunlight in the visible, and then that reflectance falls down to around 15% as you get towards the longest wavelengths in sunlight. And if you were to take an average, you would find out that weighted with the solar spectrum, it's reflecting a little less than 25% of the sunlight. So this brand new white roof over 80%, this dark gray roof less than a quarter. Well, in the middle, you can have something like this cool red roof, which I showed in a previous slide. Well, it's not reflecting as strongly in the visible, otherwise it would look white. In fact, it's got this very interesting shape to it, which translates to red in the visible spectrum. But in the near infrared, which doesn't affect color, boy, it's pretty darn reflective. So the result is this cool color, in this case a cool red clay tile, is reflecting about 40% of sunlight. So in a way, it's pretty much in the middle between the case of the dark roof and the bright white roof. And frankly, if your neighbors are going to lynch you for putting a white roof on your building, it's not a bad choice. Better than dying, I always say. So let me tell you about some of the cool colored roofs that you might see in Home Depot or from your building contractor, or just by looking around, because there are cool roofs on existing buildings right now. So you can get cool concrete tiles, and concrete tile in California, because we have this Spanish style of architecture, is pretty popular. And you can get cool clay tile. You can get cool metal. That's not as commonly used on homes, but if you were to look at the roof on, say, fast food restaurants, that's a pretty common choice. And you can also get cool-ish fiberglass shingles, or asphalt shingles, really. I'm going to talk about each, but I thought maybe we should bring up some props and do a little bit of show and tell. So Pablo, our graduate student, is going to come up here and show you a few things. So while he's bringing things up, I'm going to make an interesting point. In this top image here, I have color-matched versions of standard concrete tiles and what we call cool concrete tiles. Now, they've been designed to look exactly the same. But let's look at this extreme case of a black tile. Well, a typical black surface made with ordinary black pigments, like carbon black or iron oxide black, those are things that, if you see anything that's black, it's probably one of those two. Well, it reflects maybe 4% of sunlight. Almost nothing reflects 0% of sunlight unless it's something we call a black body cavity. But ordinary black surfaces, they bottom out around 4% reflectance. Well, if we go instead for a cool color, in which we are trying to maximize the reflectance out here in this near infrared spectrum, we can do a lot better. In fact, we can make it reflect over 40% of the sunlight. So we've got a boost of 37 points in reflectance. The darker the color is to begin with, the more improvement you can attain with a cool color. And now we're going to have Pablo do a little bit of show and tell, and why don't you talk about what we've got here?
Okay. So here, these two right here on your right are the asphalt shingles.
Why don't you go ahead and hold them up?
Yeah. So these right here have a solar reflectance of 26 and a thermal emittance of 91.
We'll skip the emittance. It's okay. We don't need the emittance.
Yes. Solar reflectance?
Yeah.
Solar reflectance of 26. And which is the same solar reflectance of these asphalt shingles right here.
That 26 is 26 points or 26%, or a little over a quarter of the sunlight.
Then we go to a metal, this green metal, and solar reflectance is 41, which is higher than asphalt shingles. And then we go to the clay tile. This is the clay tile right here. And the clay tile has the higher one, solar reflectance of 52. Right. And then these two right here are concrete tiles. They're heavy. And the solar reflectance is 0.17, 17 and 20%. 17 and 20%. These are concrete tiles. And the least one, this is the best one. This white one right here is a membrane.
Yeah, that's it's a roofing membrane.
And the solar reflectance is 88. That's what we all need to have.
Excellent. You see, we work on hiring strong graduate students. So let me, go ahead, you can take them down. We'll have some props out by the, there's a table near the entrance, so you can look at some of these things after the talk. Well, one of the interesting cases is that fiberglass asphalt shingle. Why? Well, it's the most common roofing product that goes on homes in North America because it's the least expensive. Now, the surface of a roofing shingle, it's fiberglass, it's soaked in asphalt, now it's waterproof. But if you just had an asphalt surface on your roof, there are a couple of potential problems. First of all, it's black. It would mean all your roofs would be black, and people don't necessarily want to see a black roof from the street. The other problem is that asphalt tends to crack, mostly from the ultraviolet radiation and sunlight, also a little bit from the visible. So there's crushed rock that's pressed into the surface of that shingle, and that crushed rock has two purposes. First, it protects the asphalt, which is your waterproofing, from the sun, and also it makes it look something other than black. Well, if you've got crushed rock on a surface, it's going to be a rough surface, and any rough surface is always less reflective than an equivalent smooth surface, because when light bounces off of a smooth surface, it just escapes. When light bounces off of a rough surface, some of that reflected light has a chance to take a second bite at the apple, so to speak. It could be reflected back to the rough surface. So absorption of rough surfaces is always less than absorption of an equivalent smooth surface. Also, these little bits of crushed rock called granules, they're very small. They're maybe 0.5 millimeter to 1 millimeter in diameter. And it's hard to get a thick coating on something that's small. So there's a pretty thin coating on a rough surface. But there is hope. So let me tell you a little bit about the cool roofs of tomorrow. I've already demonstrated that you can get cool concrete tile, cool clay tile, cool metal, and to some extent cool shingles. But since asphalt shingles are really the 800-pound gorilla of the residential roofing market, we would like to either offer a better color palette or higher reflectance, or maybe both. So up here, these are today's cool asphalt shingles. And they're certainly better than an ordinary asphalt shingle. A typical shingle on your home now might reflect 10% of sunlight. So going from 10 to 25% is a significant improvement. But we have a new prototype process. It's really a different way of applying colorants to the granules. And all of those in this green box here reflect at least 25% of sunlight. So they're all at least as reflective as these brownish and gray samples here. And you can see we've got reds and we've got greens and blues. So just in that alone, we've expanded the color palette. You've got more color choices now. A lot of these will reflect at least 35% of sunlight, or up to 35% of sunlight. And if you're willing to go with a bright white shingle, because maybe that's fine with you, then this one down here in the corner, which I'm showing enlarged here, well, this one reflects 62% of sunlight, so well over 60%. That's pretty good. Now, these are still in development in the laboratory, but we've been working with roofing manufacturers, and we hope over the next few years to bring that to market. The other really important area in which cool roofs can get better is we can try to keep them clean without active maintenance. I've got a picture here, and these are two side-by-side roofs in Florida, and they've been outside for 9 years. And the upper one is a white painted metal. It's a fluorinated polymer. It's a lot like Teflon in its characteristics of dirt resistance. And the lower one is a elastomeric coating over a plastic membrane, a lot like this. And this began as a bright white roof, but after several years, never mind 9 years, it's gotten grayish. And if you were to go look at exposed white roofs, you'd see this is pretty common. The initial reflectance might have been 80%, but after a couple years, could be 55% in this particular example. Well, what if we could redesign this really common kind of white roof to stay as clean as this less common metal roof? Metal roofing is somewhat more expensive than plastic roofing, so it's just not quite as common. Well, the first thing to understand is that those plastic roofs, being plastics, have agents called plasticizers, which can leach to the surface. Well, these leached plasticizers are sticky, which tends to attract soot and soil blowing in the air. They are also very nutritious if you are a microorganism. Things grow on these. And that's why a white roof might, especially in a climate like Florida, turn pretty black after a couple years. So that's no good from our point of view. We're not trying to feed the microorganisms, even though it is a kind of a safari today. Now, there are agents that you can add. These are called photocatalysts that, when they are exposed to sunlight, will help break down oils and other things and soot that make roof dirty. Photocatalysts are already used to help keep windows clean. It's pretty popular in Japan. So we can try to add photocatalytic self-cleaning to roofing surfaces like those white membranes. And as another fun thing, when you add these photocatalysts, you can change the way that water flows over a surface. So in some cases, especially for a pitched surface, you might want the water to sheet down the roof so that it carries off dirt. So we can modify those properties as well. Now, the bottom line is that if we were to go to these cool colored shingles, we could improve the energy savings that we get from cool shingles by 60%. And if we could go to cleaner white roofs, we could increase the energy savings from a cool white roof by 70%. And that's nothing to sneeze at. So that was my little tour of cool roofing. And now I'm going to turn this back over to Mel, who's going to talk about cool pavements.
I just will say a few words about some efforts to make pavements cooler, because they are a significant fraction of the city. It's surprising how much. I think I showed before that it might be as much as 35, 40%. It depends on the city, but that's about right. Because pavements include, of course, not only your streets, and you have also parking lots and driveways and sidewalks and so on, as we'll see. But the first thing you have to understand about trying to change the reflectivity of pavements is that they are a composite material. What you really have here is what we call aggregate. Namely, it's rocks of various sizes, a gradation of rocks, such that when you piece them all together, they can form the shape that you want, go around curves and so on, and have a nice, correct shape. So you start out with this array of rocks, and then you have to hold them together. Otherwise, you have a gravel road, which is not particularly satisfactory for our high-speed travel. So we have to glue the rocks together, rocks and sand and stuff, and make a nice, firm, hard surface. So in order to do that, you coat each grain of rock or each piece of rock with a binder of some sort. Now, in the case of so-called asphalt concrete, what it's saying is that the binder is asphalt, which is a petroleum product. It's this black, sticky material, which when it hardens is a very powerful glue and holds the rocks together, and you make an asphalt concrete, asphalt being the binder. We typically call that asphalt, but it really is a concrete, meaning that it's this composite. On the other hand, we have the possibility of gluing the rocks together with cement, a mineral. It's a mineral product, not a petroleum product. And that cement, those kinds of roads we call concrete. I don't know why they pick concrete for the cement concrete and asphalt for the asphalt concrete, but that's the way we speak of it. So I may kick back and forth between calling it an asphalt road or a concrete road, but they're both composites. But the key thing is that because you're coating each grain, or you're trying to, in order to glue it together, what you see mostly is the color of the binder. So, mostly. So, for example, in the asphalt road, you're seeing the color of the black tar or asphalt. In the cement concrete, you're seeing the color of the cement that you use, which typically is much lighter colored. It's a mineral sort of like limestone or something like that. So it can be much lighter in color. That's the key thing. So again, our target is the binder, if possible, because that's what shows at first. Now, of that third of the city that is covered with pavements of various kinds, about 50% are streets that we ride on. There is exposed parking. That is not in garages and stuff like that. This would include your own driveways, parking lots, malls, what have you. Quite a bit of parking area, 40% of that 35. And 10% are sidewalks, which are typically cement concrete. But these other roads, typically, as you know, are asphalt roads, asphalt concrete, which, as we know, are dark. So because these constitute about 90% of our exposed pavement, our real target is to try to make the asphalt concrete lighter colored if we can. And we can also take a crack at the cement concrete, but it's simply a smaller target. So what are we starting with? We start with fresh asphalt concrete, as Ronan mentioned, a typical black surface. And what's scary is that when people put on a new driveway, they want to make it blacker than black, so they even put carbon in there to make it, see my nice black driveway? So the reflectance is only about 5%. 95% of the sunlight is absorbed in this fresh asphalt concrete. But as it ages, as Ronan mentioned, ultraviolet light will break down some of the darkness of the thing, change its color. Also, dirt falls on it, and various drippings from your car or what have you. And it's typically, its solar reflectance goes up to about 15%. So that's what we start with. Now, the question is, can we do any better? With a new pavement, a new asphalt pavement, one thing you could do, well, you got a problem because you try very hard to coat every grain with the asphalt, so it starts out black. But on the other hand, if you do put in a light-colored aggregate, as the binder wears off, as it will, because it's kind of soft stuff, and eventually the light-colored aggregate will show through. And as you know, these roads gray out, as I showed you before. So it's partly due to the exposing of the light-colored rock. Or in some places, like near the seashore, they can use seashells. Say that 10 times fast. And because these white seashells can actually be put in as part of your aggregate. Or porcelain. I mean, you can break up toilet commodes and break them up into small pieces and put them into your roads, and they do. So these white aggregates can be useful in making lighter colored new pavements. On the other hand, for an old pavement, which would require maintenance and recoating, resurfacing periodically, roughly 10 years, it's possible to do something. There are various things you can do, but one of the simplest is you put on a layer of asphalt emulsion, which is again, this tarry material. But if you don't stop there and you put the aggregate on top, which you really want to do because the tar itself can be rather slippery. So you can put rocks on top of that and push them into the surface. And so the new surface, this new refinished surface, shows the color of the rocks right from the start. That is called a chip seal because it's a seal and you put these chips of rocks on top. Now the big issue with roads is that this aggregate is heavy and you don't want to ship it very far because then the cost of shipping it from the quarry where they mine the rock to your location can be very expensive. So you really try to use, for practical purposes, rock that is nearby. And it may not be white, it may be blackish. But the point is, if you have a source of white rock nearby, and it's the same thing, a dark rock and a white rock, use the white rock, and you will gain the benefit of having a cooler road, which protects the road actually, because if the road stays cool, it doesn't rut so much. We have data showing that if you ride over a hot road, it deforms more, as you would expect. And so the road gets ruined faster if it's hot. So there are limitations, practical limitations of availability of good aggregate, but if you have it, use it. Now here's an example in San Jose, our neighbor city. They happen to have a quarry nearby that has pretty white colored rock, and they use chip seals there. And we went out and took a picture of one of the intersections of a side street with the chip seal. And there's another one over here where this car is trying to get on the road. And here they blacktopped the road here. So you can sort of see the contrast. This is probably some older gray blacktop road. But you can see there's a striking difference in color. This road would be a lot cooler. You could walk on it maybe with bare feet. On a hot day, I think I would stay off of that one. So this is one possibility. There are others, but lack of time will have to pass over them. The other type of road, as I say, a little less common, is cement concrete. And as we say, it starts out, because the cement itself tends to be rather light colored, it starts out with a solar reflectance typically about 35%, which is pretty reflective. So a new road would look like that. But as time passes, dirt falls on the road, oil, this and that, tree droppings and all kinds of stuff. The road tends to get darker, and its solar reflectance goes down to about 20%, say. Depends on the location. But can we do anything even about this? Well, yes. One of the things you can do is simply use what's called light-colored fine aggregate. It turns out that when you make the cement road, the fine aggregates, the little sandy stuff, tends to float to the top. So if you make that whitish, you forget about maybe the large aggregate, but if the white fines are light-colored, you can go from maybe 35 to 40%. You can gain something. There's another thing, which is slag, which can be used as replacing part of the gray cement. This is a byproduct of steel production, but it turns out it makes a quite good cement. And if you put in about 50%, you can get an initial solar reflectance of about 60%. It's quite good reflecting. And there also is possible to find cements which have very few colored impurities in them. So you can actually make a very white cement. And if you build a road out of that kind of cement, its initial solar reflectance can be as high as 70%. Then, of course, it will degrade in time. So there are possibilities for making even our roads whiter and more reflective, and therefore the city a little bit cooler. And now I have the honor of introducing Art Rosenfeld.
Okay. I can barely see you. I have cataracts, which are pretty good when there's not a lot of ooh. But anyway, I assume you're there. Hi. So I'm going to take over at this stage of the game and bring us into modern times with a real problem of global warming and ask the following. 2,000 years ago, when there were buildings, it became important to ask, how can I keep my building cool? few hundred years ago when there were large cities, the question was, can I figure out how to keep my city cool? And now the question is, can I figure out how to keep my planet cool? Before I do that, I want to whiz around the world and show you that you can have a lot of fun with Google Earth. I'll get to my picture of the Pentagon in a moment, but that was fun. Ronan showed you this example of sloped roofs, which are popular in Bermuda because there aren't a lot of big rivers on a small island. The rainwater is short. People collect it on a nice, clean, white roof and use it for their water supply. That's a Greek island. There, it's so popular that even the sides of the buildings are cool. Going to set my watch. Okay. That's Hyderabad. In India, when it isn't raining, people like to sleep out on the roof, and if the roof is stayed somewhat cool during the day, then it's not so darn hot at night. And so white roofs are getting pretty much in vogue. That's a Walmart store. In 2005, Walmart looked into the economics of white roofs to save air conditioning and because they last longer than dark roofs, and decided it was time to switch. They've done 4,500 of these box stores so far, including overseas. They got 1,500 to go. The competitor here, who shall remain Walmart-less, I'm sorry, whose name shall remain, shall remain, has since switched. And in fact, all the box stores are going in for white roofs. That's UC Davis. I might mention, I'll say it in its appropriate place before, but since 2005, the Energy Commission's Title 20 New Buildings and Retrofit standards have required that if a roof is flat, as Ronan said, no visible architectural issues, it shall be white. That's in the commercial code. It will go into the residential building code, which still have a number of flat roofs, in 2012. So that's what a modern city is looking like from a satellite. That's the University of Tucson in the middle. Nice white roofs or some nice cool colored tiles. But notice now that the residential areas around the side of this quadrangle are mainly white because people know in Phoenix and in Tucson that it's really hot, and Ronan Ranch in Florida. Speaking of Florida, that's modern, probably a lot of retirees with their nice white sloped roofs. They're not scared of them, and boats on the marina. That's Washington, D.C., which, as the caption says, has some problems. There are some whites. There's the Dome of the Capitol. There's the Supreme Court. There's the Library of Congress. But when you get to these House and Senate office buildings, they're all green. They can't be seen from the street. I have some friends who are worrying about that now. This is sort of interesting. This nice white building is the aerospace building, which puts to shame this roof here, which is the national headquarters of the Department of Energy. I showed this slide at a symposium in Berkeley and in Davis in February. And later on, the Secretary of Energy called me up and said, "Art, you'll be happy to know that I'm putting out a memo in June that all DOE roofs and replacement roofs shall be white, and the Forest Oil building is going to be done in October or November." And the Marine Corps Commandant announced that his roofs were going white or vegetative. And then there was a sort of amusing moment in which all these admirals and generals were trying to figure out whether they could really convince the Corps of Engineers to go white. But I think they will. So that's my, this white area here I thought was modern Pentagon philosophy. This turns out to be metro station. Okay, what about the Earth? Let me remind you that part of the temperature of the Earth right now is determined by ice and snow. We have a Greenland ice cap, which is decreased in size. We have Arctic sea ice, which is decreased in size. If we can add a little bit of white, that would be useful. Cities now comprise about 2% of the world's land area, which incidentally means they cover an area about the size of the state of California. And it would be nice if we could make some of that white. So this is not to explain, Melvin Pomerantz has gone through it. I just want to say the words again that we're getting into. This is incoming sunlight. The more of it you can make bounce up and escape through the transparent atmosphere and go back into space where we would like it to go, the better off we are. If it gets absorbed, it gets degraded into heat, and then it gets trapped by the greenhouse effect. And if you stop to visualize this, there are lots of greenhouses, particularly around the Mediterranean, where they work very well in the winter, thank you, and they tend to overheat in the summer. And greenhouse managers all know that you then whitewash the glass on the greenhouse. That reflects the light as light, and it doesn't get into the greenhouse, and it doesn't make the plants overheat, and it works fine. And so that's what we're trying to do. Now, atmospheric climatologists have been aware of this issue for years, and back in the 1980s, when cities occupied maybe 1/4 of the world's land area, Jim Hansen published a paper asking whether cooling cities would make an appreciable difference in the greenhouse effect. He got an answer less than 1/10 of a degree. And we weren't so scared those days. And so, well, that was a hard sell. All that started this current furor over white roofs is just a small calculation which Hasham Akbari, Ronen's former boss at the Heat Island group at Lawrence Berkeley Lab, and I and an Indian friend, asked, maybe there's a better way to sell this. 1/10 of a degree actually isn't crazy, since we're going to spend trillions of dollars and break our backs trying to keep it down to 2 degrees, but it's still not a good sell. So we asked instead, look, carbon dioxide reflects heat, and that's called a positive radiation forcing onto the ground. And white roofs reflect heat. And let's set the two equal and see how much CO2 heating we've offset with a questionable number of tons of CO2. Well, the advantage to that is the carbon dioxide has a price. It's interesting, we're trying to control the temperature. We do it through carbon dioxide, but of course it's the carbon dioxide that has the price and not the bad product, which is the temperature. But that's the way air quality managements go. So we got to do it per unit. I could give you the answer in per square foot, but it wouldn't be a good sell. I can give you, to make things sound a little more plausible, the amount of carbon dioxide emissions offset by 1,000 square feet, which is the size of a modest house without a garage, although we're talking mainly about commercial space. which is 100 square meters in technical units in System International. And that turns out to be 10 tons of CO2. Well, now that's a little more interesting. CO2 is trading on the European exchange for about $25 a ton now, so 10 tons is 250 bucks. That's enough to begin to make an incentive for actually doing the right thing. Supposing we now multiply this 10 tons by about 3 billion, because there are about 3 billion of these units of roof in urban centers where white roofs are already useful, if you've listened and been convinced by my two previous colleagues. Then it turns out that you save, or you avoid the heating effect of, you offset the heating effect of 25 billion tons of CO2. That's over the life of the roof, and it's hard to figure out. It would be equivalent to turning off the world, the whole world, all the emissions, annual emissions of the world for 8 months. But that's not conceivable to me anyway. We have to turn it into some sort of a rate. So I'm going to take the 25 billion tons and say the roof lasts 20 years. So that's over 1 billion tons a year. What does 1 billion tons mean? Well, now we got it per year, and we can say, we can compare that with familiar things, like your house emits about 10 tons a year, or your car emits about 5 tons a year. And cars worldwide probably are a little more efficient than American cars, so let's say 4 tons a year. Well, that turns out to be 300 million cars off the road equivalent for 20 years. There are only 600 million cars on the road right now in the world, so that's half the cars in the world off the road for 20 years.
Art, slides.
What, did I say something wrong?
No, you're fine, but you got slides.
Oh, next slide. Thank you. There we go. And luckily, I'm an old friend of Steve Chu's, the Secretary of Energy, who was familiar with this calculation before he became Secretary of Energy and has been noising it around the world. And one sentence from Steve Chu gets as much publicity as a lecture to you folks from me. So we're embarked in a sort of worldwide campaign to try to convince developing nations who are building like mad to put white roofs into their building standards. This is, the cars are going to disappear. Ronan is good at PowerPoint. Thank you, Ronan. So what to do now seems to be, first, to try to get other states to follow California. I'll tell you what that means in a moment. But I guess I better tell you right now. I'm going to repeat the present state of building standards in California. And I said that starting in 2005, the commercial code was modified to say a flat roof shall be white, and most roofs are flat, so that's really a good summary of the code. In 2008, the residential code was addressed, and for the 5 hottest climate zones, we have 16 climate zones in California. For the 5 hottest climate zones, it was required that sloped roofs, visible from the street, shall be cool colors. It didn't pay yet to go into the Los Angeles basin, but that's next. And the prices will come down. Right now there's a shortage of cool-colored roofing materials because of the standard, but prices will come down as volumes go up, and that will spread across the states. And I'm going to not have time to talk about this now, but maybe during the question period it will come up. But California is revising its building standards to include this so-called externality of CO2 on all its building optimizations. So there's Title 24, there's cool-colored roofs. Arizona and Florida and Georgia have followed suit. The problem is most of the United States, the hot part of the United States, let's say, well, I lived in Chicago for 10 years, and I would say Chicago summers are pretty hot. You saw that sea of black roofs that you saw earlier on row houses. And as far north as far south on the continent as maybe Sao Paulo. United States relies on model building codes put out by outfits by the strange names of ASHRAE and IEEC, International Energy Efficiency Code. And states are not required to adopt them. States can make them stronger and adopt them. States can some states, Texas is still, has no codes whatsoever except for the cities who've taken the lead. So it's important to beef that up. And DOE is busy figuring out how to exert a little more pressure on the states to get modern. ASHRAE and IEEC will prescribe white roofs in their next editions. They come out every 3 years. The situation is really quite encouraging. It's getting a lot of momentum. EPA, Ronan showed an EPA list of cool roofing materials. That's been available since 2005. DOE is going white, as I said. The Marine Corps is going white, as I said. Dow Chemical started a competition in Philadelphia, and the block that won out of 2,700 blocks that participated, every house on the block volunteered to accept a white roof courtesy of Dow Chemical. We're going to, my last point is we're going to launch a private club called 100 Cool Cities, in which we are going to, with some DOE help, approach the 100 largest cities in the world. That gets you down to a population of about 2 million. And ask them if they would like to join to be willing to at least address the problem of cool roofs, convince themselves that it's cost effective to do that, put it into their building standards, and think about enforcing their building standards. In next spring, Secretary Chu is going to a semi-annual meeting of the energy ministers of the G20, which is the group that the United States belongs to, which is trying to make offers, voluntary offers, to do something about climate change. And he's going to offer technical assistance to any country, or let's say the first 5 countries, which will sign up to address this issue. And, whoops. Phooey. Forget it. The next slide we won't show.
Hit the down arrow, Art.
Did it. And so this is the environmental groups whom we hope to coalesce together in this whole 100 Cool Cities program. This is the Sierra Club, which has a number of offices around the world now. This is the Clinton G40 collection of 40 offices in the 40 largest cities of the world who want to collaborate with us. This is the Energy Foundation, whom we want to get some money from. Alliance to Save Energy, U.S. Green Building Council, ICLEI. Is Nancy Skinner here? ICLEI, with whom Nancy Skinner worked for years. The Climate Group, the American Council for Energy Efficient Economy, and so on. So we have great hopes, starting with this initial help from the Department of Energy. So there are things we can do, but California has one last thing you can think of. The Title 24 building standards are doing 90% of the job for us. Over 20 years, California flat roofs will go white. In California, it's so sunny that it actually pays, in many cases, to take a roof which is not leaking yet, which is not needed for repair, but still has, let's say, 10 years of life or more. And it turns out you save so much electricity from a white roof that it pays to go ahead and whiten your roof, even though it's relatively new. Now that's something that those of you who have some control over the buildings you work in may want to suggest to the facilities manager to look into the economics. So things are moving along nicely, and thank you very much.
Is it working now? It seems like. Thank you very much to Art, Ronan, and Melvin. I'm sure there's lots of questions, and I'll kick off the Q&A portion by introducing and then handing the mic to Assembly Member Nancy Skinner, who's with us in the audience today. She's been a leader on a number of climate change policies initiatives since her time on the Berkeley City Council, and is founder of the International Council for Local Environmental Initiatives. She continues to lead on a wide range of environmental initiatives as chair of the Assembly Rules Committee, chair of the Select Committee on Renewable Energy, and member of the Natural Resources Committee, among other capacities.
Thank you. And we... No.
I just came off 10 years of the Energy Commission. The last two, Nancy was there, and she got more legislation than we needed done in those 2 years than we got done in the previous few. It's been a great pleasure.
Well, and we have to salute Art for being the person who made sure that in our Title 24 in California's building code that the white roofs is now there. And actually, it's really refreshing to be home in Berkeley and to listen to scientists rather than the hot air I often hear in Sacramento. And my question is, and Art, you already stole some of it, but I was going to ask you, given that I'm a legislator and you know, I have some influence over California policy, what is it that people like me can do to make California cool? And I think you just answered about roofs, but perhaps you or the other panelists could talk a little bit about pavement.
What can I say except you're 100% right. The Caltrans, well, the problem is it's fine for Mel Pomerantz to appear in Berkeley and point out the advantages of cool pavements. But unless Caltrans gets behind it and issues documents and white papers showing that, in fact, the life cycle of concrete roads is better anyway than asphalt, nobody will pay any attention. City councils are used to listening to Caltrans or the U.S. Department of Energy and not to us scientists, and get a line item in the budget for Caltrans to address white roofs. I'm sorry, cool pavements.
Hi, this is actually for Dr. Levinson. I was wondering about...
Where are you?
Over here. To your left.
Yes,
Sorry.
okay.
I was wondering about comparing solar paneling on roofs and the energy savings and the environmental savings, comparing that to white roofs. Like,
Sure.
How would they be compared?
Right. Well, the thing is that solar panels are pretty expensive. You're looking at on the order of $10,000 per kilowatt of power that you get, and a large home might be on the order of a 10 kilowatt system. So you're looking at an investment on the order of $100,000. Of course, it could be less if you're requiring less power. To go from an absorptive roof to a cool roof, a reflective roof rather, can cost nothing if it's time to replace the roof. And in fact, in many cases, you can do both, because you'll typically want to, if you're going to have some solar panels on your home, you want to put them on the, if it's a pitched roof, on the highest parts of the roof, those that are not going to be shaded so much. And you're not going to usually occupy the entire roof with solar panels because it's something...
20% is the average.
Yeah, so about a fifth of your roof. in fact, what we commonly see right now on commercial buildings is it's a combined approach where when it's time to put on new solar equipment, they will put down a white membrane roof into which solar panels are built in and occupies some fraction of that. It's called a building integrated photovoltaic. And if you look at some aerial pictures, you can see a fair number of those. If you're going to put a PV on your home with a pitched roof, it would probably go towards the crest of the roof. So cool roofs, almost free if it's time to replace the roof. PV's pretty expensive, but there's room for both.
Good evening. My name is Bruce. I have a question and a comment about a gadget. The question is that maybe 10 or 15 years ago, there were people who discovered that the Lotus plant has little hairs on it, and companies which were making paint, which they tried to sell to me in Germany, which would stay clean because the dirt would wash off. And I was just wondering what the present situation is for this for this type of covering. It wasn't thought of being necessarily white, but just to keep clean. And the comment is that this little gadget here is an infrared telescope. It's a thermometer, and the idea is that you can take an infrared measurement of the. If you go to buy your tile roof from a man who puts it out in the sunlight, then you can go around and just see which one has the lowest temperature just by. And so the temperature of the roof here is 22.5 degrees Celsius. A colleague here's temperature is about 29 degrees through the sweater. And so you can use that for shopping. But what's happening with the Lotus wallpaper or house?
Sure. Actually, I'm not an expert in that, but I did see a colleague show some interesting properties of some plant surfaces. Truth is, I don't really know about that. I will make a comment about the infrared thermometers, which what you're describing is that those are very commonly available in hardware stores. So if you were kind of curious to know how hot is that wall or roof, or even the painted surface of a car, it's a very easy way to measure surface temperature. Actually, it's a lot easier than using a contact thermometer. So people will also use infrared imagery to understand how much heat is leaking through the shell of their building. So, for example, people in winter might want to know where are there gaps in the insulation in my wall or in my roof, and they'll take an infrared picture, and where they see hot spots are typically where heat is flowing from the inside of the building to the outside. So infrared thermometry is in fact a really good way to try to understand what's going on in your building.
I have one comment which is slightly tangential, but occurs to me as being worth mentioning. One of my thousands of slides I didn't show is two Priuses which are parked outside of an exhibition center in Tokyo last year. They're both blue, looking identical. One is cool blue, one is regular blue. And the cool blue one runs skin temperature 18 degrees centigrade, so 30 or 40 degrees Fahrenheit, cooler than the other. If all cars did that, well, I will finish the sentence and then correct myself. If all cars did that, you could downsize the air conditioner and save on the first cost of the car. Now, actually, the manufacturers are a little scared of cool-colored paints because they have a white undercoat under your beautiful new red or blue cool color, and they show scratches worse. But I assert that the roofs of cars have very few scratches. I've never seen a parking lot incident where the roof of a car got scratched. I think Morris Mini got that idea some time ago. If you don't specify the wrong color, they will supply your Morris with a white roof. You may notice that all school buses in California, in fact, all passenger buses in California have white roofs. I was in India recently on a non-air-conditioned train which was stinking hot, had a blue roof. So one of the things I talked over with the Minister of Transportation was Indian trains should have white roofs. But there are lots of applications, actually, of common sense to things other than the roofs of buildings.
I have a 20-year-old asphalt shingle roof that doesn't leak or anything. And I was contemplating painting it, not myself, but painting it with white. And if so, is there any special paint that you should use? And then a side issue to that, once you have the white roof, do you have to heat a little more in the winter because it's reflecting the sun away?
I'm going to take one of those and give the first question to Ronan. I'm very glad you asked that question about heating. And at first it sounds like a serious question, and in fact, I heard one admiral dismiss the whole idea because of the winter penalty. This is one place where the law of perversity fails. In the summer, the sun is high in the sky, and it sees mainly the roof, and doesn't care about, barely sees the south wall. In the winter, at our latitude, United States latitudes, the sun is low and sees mainly the south wall and couldn't care less about the roof. So the winter penalty is something we put into the economics. Ronan is the author of a paper which calculated the winter penalty for 16 climate zones. And the winter penalty runs from 5% in Louisiana to 25% in Fargo, North Dakota. Although I'm not greatly selling white roofs in Fargo, North Dakota. But the winter penalty is well known, put into the economics, and not serious. Now, Ronan, there was a...
Sure. Let me just one or two more things on that part of your question. First, when we figure out what's the value of the energy savings that you get, for example, some of those numbers that I showed before, well, what that is, that's the value of the savings of air conditioning minus the extra cost you're going to incur from additional heating that might be required in the winter. So we do factor that in already. One of the fun things to notice is that on a horizontal surface, a typical low-sloped roof you might have on a commercial building, well, as you go further north, say north of 40 latitude, so we're talking about, roughly upper third of the U.S. We're at 37 north right now. You get about 3 to 5 times as much daily sunlight in summer as you do in winter. For a couple reasons. The sun is low. Also, the sky is pretty cloudy in winter. So there isn't that much sun available to heat your roof in the winter in the first place. So you're not losing that much sunlight. Also, once there is snow on your roof, it doesn't matter what color the roof was. Your roof is white. That's right. Well, actually, every part of the U.S. is different. We did this exhaustive study around the U.S. to try to figure out what would the savings be, your net savings, and we've got some lovely maps that we can show you, but I didn't want to take up the time right now. But it turns out that in virtually every part of the U.S., putting a white roof on a commercial building instead of a gray roof saves you money. Even in places that are pretty far north, even in most of Alaska.
But don't try selling it.
Right, but we're not that excited because in places like Alaska, there might be some net savings, but it's a very small net savings, so it really wouldn't matter much. Kind of like Berkeley. You could put a white roof on your building in Berkeley and you might get some savings, but it wouldn't be that much because you don't need that much air conditioning here. That's why we live in Berkeley. Now, about your really practical question about what to do with your 20-year-old shingle roof. That's mechanically sound, right? You don't want to get, yeah. Now, for most kinds of roofing materials, you can coat them. The one that's in dispute is unfortunately the one that's most common on homes. Argument goes like this. Yes, you could take, there are special coatings, by the way, for roofing products. You never want to use exterior house paint. That's meant to stick to wooden walls. Wooden walls don't have a lot of water standing on them, and they're not asphaltic. So, also, when you put on ordinary house paint, it's a pretty thin layer, even exterior paint. When you're putting a coating on a roof, like some of those white horizontal roofs that we showed before, that kind of coating is about 5 to 10 times thicker than a typical exterior house paint. And you can go buy them in a Home Depot. They're called elastomeric roof coatings. Now, before you put this on the roof of your home, there's a bit of a debate going on between the companies that make these elastomeric coatings and the companies that make roofing shingles. And the people that make roofing shingles say, well, look, my roofing shingle, it's not one continuous surface. It's a bunch of shingles nailed over each other. And they allow the building to breathe. That is, gas can move through the little spacings between the shingles. If you put a solid coating over it, my roof can't breathe anymore and it's going to fail earlier. The people that make the coatings say this is nonsense. The people that make the shingles say, well, you can call it nonsense, but you're going to void my warranty. So at this point in time, I do not encourage people to go put elastomeric coatings on shingle roofs until that dust settles. Maybe it will settle one day. For all other kinds of roofing products, though, for example, tile or metal, you can certainly go recoat them if they are, say, darker than you want right now, and you want to have a cool color or a white surface. There's no mechanical issue there. There's no voiding of warranties. Well, actually, you'd be surprised. They are prorated, so they fall down in value, but lots of shingles today are sold with 40-year warranties. Of course, I'm not sure that I would expect the company to be around in 40 years, or even know where the papers were after 40 years, but still.
So what is the solar reflectivity of a green or vegetated roof in comparison to a white roof? I'm curious, I know it costs more, but then it also has the capturing rainwater, preventing stormwater effect.
Sure. So a typical vegetative roof, it depends exactly what the vegetation is and just kind of how rough the surface is. We can say it's ballpark 20 to 30% reflective. Now, that is unfortunately quite a bit less reflective than even a soiled white roof, because a soiled white roof is reflecting 50 to 60% of sunlight. However, that doesn't mean that you shouldn't go for a vegetative roof. They're just different considerations. Going for a light-colored reflective roof instead of a dark roof, that's really just a choice of the surface properties of that roofing material. And if it's time to get a new roof, it's not that much harder to choose a reflective roof instead of a darker roof. If you want to go to a vegetative roof, the first question is, do I have a roof that is strong enough to support it? In climates where there is snow in winter, the answer is usually yes, because the roofs are meant to support snow, which is quite heavy. In places that don't have snow, the construction often really can't carry that extra weight. In fact, that's one reason why people might have a fiberglass asphalt shingle roof on their home instead of a tile roof. The shingle roof weighs a lot less per unit area. But there are other benefits to vegetative roofs that you don't get with simple impermeable roofing surfaces. For example, stormwater control is a popular reason to install a vegetative roof, because water goes into the soil instead of just running off an impermeable surface. There's also some evaporation of the water from the vegetative roof, and that will reduce the temperature of the outside air while, however, making it more humid. So sort of a big picture, if what you want to do is keep your building cool, then both a reflective roof or a vegetative roof, which is somewhat reflective but not super reflective, will help in that regard. For a vegetative roof, you're going to need to make sure that you've got a strong roof, can hold the weight of that soil system and the vegetation, and you're also going to have to make sure that your vegetative roof stays alive. There are many cases of roofs that were planted and then a couple of years later are just sawed with dead plants on top, so got to be careful. But the other big picture thing is that if you're trying to keep the planet cool, then what you really want to do is reflect as much sunlight as possible back out into space. Now, the vegetative roof is going to reflect 70 to 80% of that sunlight back up into space. The white roof is going to reflect maybe 50, did I get that backwards? I probably did. Sorry about that one. So the vegetative roof is going to absorb about maybe 70, 80% of the sunlight and reflect about 20 to 30% of it back into space. The white roof, when new, might absorb 20% of the sunlight, reflecting 80% back out into space. And even when it's soiled, it still might be reflecting about 60% out into space. So depends what you're trying to do.
I want to make one comment. I've actually had another hilarious set of meetings about vegetative roofs versus white roofs. As Ronan said, there are two communities. There's the extreme conservationist, environmentalist movement, which goes naturally for vegetative roofs. And they always cite exactly what Ronan just said. It's as if he read it from their literature. They sop up stormwater. Now, I always thought that all roofs collected stormwater and that it was easy to collect. So I arranged a meeting with the Federal Energy Management Program in Washington a few weeks ago, in which we had representatives from the water community and the regular builders of old-fashioned He-Man roofs, and then the vegetative roof folks. And I asked them two questions. First, to the vegetative people, if it's a good idea to sop up half the water in the medium, which is what they do, why don't you sop up the other half and avoid more stormwater? Oh, they never thought of that. The other question for the people who are going to redo the Forest Oil building, the DOE headquarters, is you're going to put on a white roof. Are you going to collect the stormwater and put it in a cistern and use it for irrigation and gray water and so forth and so on? Or are you just going to dump it on the streets of Washington to go into Chesapeake Bay? Oh, we never thought of that. So what's going to happen out of that meeting is that, in fact, the DOE advice on all roofs shall go white, because Steve Chu and I are obsessed with global warming, is going to be shall go white, but shall address the question of collecting, if cost-effective, stormwater to at least hold it to the next day when the storm is over, and preferably to use it for irrigation, gray water, and so forth. So it turns out these two communities don't talk to one another.
Question. Ooh, boy. I have a question about photovoltaics again, in terms of how cool are the appliances themselves? They're dark. You know, they look like they would absorb a lot of heat themselves. You know, you're talking about there's certain systems that actually embed them on the surface of the roof, versus, you know, others that often suspend them above the roof surface. So I would imagine there's a lot more air circulation. Could you discuss,
Sure.
you know, the appliances themselves, how cool they are?
Sure. So the first question is, how cool are they? And of course, it varies from PV to PV, but typically a PV reflects about 25% of incident sunlight, and it might convert, in the case of, you know, an amorphous silicon PV, another 6% into electricity. So that means they're going to be absorbing, in that example, about 69% of the incident sunlight and turning that into heat, rather than, say, turning that into electricity. The white roof, on the other hand, when new, is absorbing only 20% of the sunlight, and when soiled, maybe 40% of the sunlight. Now, if you have a non-integrated photovoltaic, an offset photovoltaic, which is the more traditional way of doing it, that's actually a little bit better for the building, because there isn't so much heat flow from the hot surface of the PV into the building itself. There's an air gap, so there's some flow of air underneath the PV, so it's cooled from two sides. Also, the underside of a PV is typically a shiny metal, which is a poor emitter and absorber of thermal radiation, so it's basically like having a little radiant barrier between the offset PV and the roof itself.
So it looks like we have a number of questions left, but however, unfortunately, we have time for one more. If you still have a remaining question after this one, you are welcome to try to grab a panelist at the end of the talk.
I have two questions. One regarding using lighter pavement for roadways. What would be the glare factor for motorists? And my other question is, as a honorary member of the American Institute of Architects, I started writing about this issue 20 years ago, more than 20 years ago. And why did it take the architects and building engineer industry this long to favor up to the idea of white roofs or did it take legal action to do it? Because they were resistant and rather tradition-bound in their own industry.
Well, I'll take the easy one. We have a historical figure here who can answer the historical question. The glare, I like to put it this way, that experiment is being done millions of times a day on cement concrete roads. I mean, superhighways are made of cement concrete. And I don't see people pulling off the road being blinded by the glare from cement concrete roads. So it's not much of an issue.
In fact, I'm going to emphasize that point a little bit.
Please.
I used to commute weekly for 10 years from Berkeley to Sacramento. So I know Highway 80 intimately. Despite what Mel said, if you actually keep track of it, there are many different segments, but I would say it's 1/3 asphalt and 2/3 pavement, concrete. And if you ask people, when they ask your question, what color was the freeway when you drove from San Francisco, they don't have a clue. Go ahead.
Yeah, that's a good answer. Well, the fact is, you know, even black asphalt can be very reflective. If you go at the end of the day and the sun is low in the sky, I've noticed that it can be quite glary. It depends on the angle of the sun. Even black asphalt can be quite glary. So I don't think it's really a problem. All of us have driven on these roads, and you don't get blinded. We're not talking about making them into mirrors. You know, it's going to be even 50% reflecting. I don't think will give us too much trouble. But it's a good question, and it has to be answered. And I think that the experience, our own experience, we've all done that experiment already, and I think it's okay.
Could I add
Go ahead.
Well, let me just add a little bit about reflective pavements. You can actually see right now examples of bright white pavement if you look at Jersey barriers that are used on highways to prevent people from crossing over into the median. Now, I don't think we're proposing here that highways should be as bright white as that, but there is a lot of room for improvement. What's interesting is that many roads have the opposite problem, which is that they are too dark at night. So it requires an awful lot of artificial street lighting to make it work out. And this issue, for example, for parking lots. So there are cases where there's going to be an extra benefit, never mind the whole idea of cool communities, which is reduced consumption of electricity at night for illumination. Now, Art, would you like to field the other part of that question about architecture?
The other point I'd like to make, since some of us are advancing, no, we aren't age, but you know, to see street signs, if you have a better reflecting road, the light from your headlights will reflect off the signs better, and people whose vision is not up to what it used to be can see the signs better. So there's a safety factor which may actually benefit people.
I've forgotten what the first part of your question was.
Historically, why did it take so long?
Why did it take so long?
For the architects to get with it.
Boy. What fixed it? I think I know that it took a new generation of architects who got taught something about environmental controls in their courses and not just about facades. But what fixed it was, in fact, not regulation, not legislation, but just regulation. That is, when I first started talking about the advantages of white roofs with the California Title 24 staff, they were convinced in half an hour that it was the right thing to do. And we did it, and nobody, for flat roofs where there isn't any architectural issue, nobody has really bothered to complain. The people who made a living in putting black roofing on flat roofs have presumably gone to Texas. But apart from that, and the handwriting was on the wall, I don't think there's been It wasn't necessary to inform the whole public. It's just a new tradition which seems to be working fine.
I would like to add one more point to that before we wrap up. It turns out that what architects specify and what developers offer as choices depends a lot on what they perceive as the demand from their clients. Typically a developer will be presented with some sort of a color palette for maybe a residential development, and that's what they go with. If people decide that what they want are reflective roofs, that percolates upward. And in fact, one thing that you might want to do, we've got a Cool Communities program at Berkeley Lab, and it's to encourage the voluntary adoption of things like cool roofs and cool pavements. And within about a month or so, one of the websites up there, Cool California, and you go to coolcalifornia.org, is going to have resources available to help homeowners find cool roofs if they're in the market for them. And there are actually quite a few products that are out there right now. So it's what you ask for is what you eventually get.
Thanks again to Art, Ronan, and Melvin for coming out. And thank you for coming out to tonight's event. Don't miss our final one in the fall series, Putting Carbon in Its Place, What You Can Do, which takes place November 8th, 7 p.m. at this stage, which is a couple Mondays from now. So thank you.